Good day. So today we proceed with the discussion of the analysis of indeterminate beams. So one of the most recommended procedure is the analysis of indeterminate beams, especially continuous beams. We have the three-moment equation, which was first introduced by a French engineer way back 1857. So we have this equation. So we have M1, that is the moment on the first support. L1, the length of the first span, over I1, that is the moment of inertia of the beam of the first span, plus twice moment of the second support, or that is the middle support for this beam. I multiply by the quantity L1 over I1 plus L2 over I2, the properties of the second span beam. M3, that is the moment on the third support, L2 over I sub 2. We have 6A1 A1 over I1 L1. The numerator, this is the statical moment area with respect to the left span of or left side of the beam, plus 6 area to B2, that is the statical moment area, that is for the right end of the beam, for the right span, is equal to 6 times E multiplied by the quantity H1, that is the settlement of the support measured with respect to the middle support, plus H sub 3, that is the settlement of the third support, with respect to the second support. But for cases, let's say for the cases that we have constant dimension or constant properties of the beam for all spans, let's say I1 is equal to I2, or in general, let's say EI is constant. And for the cases that we have no support settlement, we may assume that H1, the same as H sub 3, will be equal to 0. Then we can simplify this equation. So we can multiply, let's say I1 or I, for both sides of the equation. So let's say again, I1 is equal to I2. Let's say we have a constant moment of inertia of the section. So no support settlement, that makes this term will be 0. So we may eliminate all the moment of inertia on the denominator. So the simplified form will be, for this case, we have M1, the moment of the first support, L1 plus twice the moment on the second support or middle support. This is multiplied by L1 plus L2 plus the moment on the third support, L sub 2, plus this is 6 times A1, A sub 1 divided by L1, plus we have 6 times A sub 2, B sub 2 divided by L sub 2, and this is now equal to 0. So this is the simplified form. If we have constant moment of inertia, or EI is basically constant for the entire for all of the spans, and no support settlement. So let's try this example using the three-moment equation. So assuming that EI is constant and no support settlement. So for example, we have this beam, 8 meters span with 4 meters per span, continuous siya. So we have, it is loaded with 40 kilonewtons per meter. So we are required to draw the shear and moment diagram. So let's observe, so the support on the left end is a hinge support. So the moment for a hinge support, that is our M1, will be 0. Then on the right end, that is our roller support, our M sub 3 is equal to 0. So to determine all the support reactions, we need the moment on the middle support. So first step, using the three-moment equation, we are to separate the spans, then assume them to be simply supported for the computation of the statical moment area. So we have, this is 4 times 40, 160 over 2. We have 80 kilonewtons as support reactions. Then we draw the equivalent moment area Okay, for the left span, it should be with respect to the left end. So I'll be choosing this side as the fixed support. That is 80 times 4 is, we have 320. We have 40 times 4 is 160 times 2. This is a 0 degree loading. The shear diagram will be first degree. The moment diagram will be, this is a second degree curve, and this is negative 320. Alright, let us compute for the statical moment area of the left span. That is A1, A1. So all we have to do is locate the centroids with respect to the left end. That is, on the positive area, there is 1/2, the base is 4 times 320. Its centroid with respect to the left end, that is a triangle, 1/3 of 4. Okay, plus, for the negative area, there is 1, the degree of the curve plus 1, multiplied by 4 times negative 320. Its centroid will be 1 over the degree of the curve plus 2 of 4. So let's compute the equivalent of A1, A1. The statical moment area of the left span. Let's equal to 1,280 over 3. Okay, so the equivalent of 6A1 A sub 1 over L sub 1. This is 6 times 1,280 over 3. This is divided by the length of the first span is 4. That will be equal to 640. Alright, then we have to compute for the equivalent of A sub 2, B sub 2, that is on the right span. But as you can see, they are similar or identical. Okay, so this time with respect to the right end, this is the same as 80 kilonewtons. The same as 80 kilonewtons. So this time with respect to the right end. So it's 80 times 4. We have positive 320, 40 times 4 times 2, that is towards the negative area, negative 320. As you can see, a mirror reflection of the left span. So we have, this is area 2, B sub 2, this time with respect to the right end. There is 1/2, the base is 4 times 320. This is multiplied by 1 over 3 of 4 plus the negative area, that is 1 over 2 plus 1, 4 times the negative 320 multiplied by 1 over 2 plus 2 of 4. As you can see, they are equal. So usually for a two-span beam having a consistent or constant loading, these two will be having the same value. So we have the value of A sub 2, B sub 2 is the same as 1,280 divided by 3. Then we have the value of 6 times A sub 2, B sub 2, this is divided by L sub 2. We have 1,280, this is multiplied by 6, divided by the same span of 4, the same value of 640. And let us now compute for the moment on the middle support. Okay, so from our 3-moment equation, that is, the moment M1, L1 plus twice the moment of the middle support, this is multiplied by L1 plus L2 plus the moment 3, this is L sub 2 plus, we have 6 times A1 over L sub 1 plus, we have 6 times A sub 2, B sub 2 divided by L sub 2 equal to 0. So again, and supports are simple supports, moments are equal to 0. That makes this term 0, okay, 0. So let's compute for the moment. number 2. So we have 2 times n sub 2. Span number 1 is 4 meters plus 4 meters, span number 2. Okay, plus we have this value is the same as 640 plus 640 equal to 0. So let us compute for the value of moment number 2. And is equal to, we have negative 80 kilonewton meter. So that will be the moment on this point in the middle support. So let us compute for the support reactions. So we have, we may cut this section on the middle support, cut and expose. So let's say this is point B. Since we have a roller support here, so the direction of the moment should be like this. We have, if we have to separate that from the portion of the ruler, so we have the computed moment is counterclockwise. This is negative 80. So let's say we cut the beam just before the ruler. So therefore, if we are to consider this span, we'll be having, if this is counterclockwise, we assume this one to be clockwise. Or this is 80 kilonewton meter. But the actual moment on the support is a negative bending moment, negative 80 kilonewton meter. So this, the loading is 40 kilonewton, 40 kilonewtons per meter. So we are computing now for reaction number 1 and the reaction number 3. But as you can see, we have a symmetrical loading or continuous, consistent or constant loading. R1 is the same as R number 3. Obviously, the support reaction on the left end is equal to the support reaction on the right end. So we may do, for example, and the summation of moment at B equal to 0, clockwise moments to be positive. That is, we have R1 times the span of 4 meters minus 40 times 4 times the lever arm will be 2 plus 80 is equal to 0. This is 80 kilonewtons considering this span. Okay. For example, we cut the beam over the ruler support. Okay, but the actual moment on that portion is actually a negative bending moment. So we'll be having reaction number 1 that is similar to reaction number 2, or basically equal to reaction number, should be not number 2. Reaction number 3. This is equal to, we have 60 kilonewtons. So we have R1 is equal to 60 kilonewtons. R number 3 is the same as 60 kilonewtons. So let us compute for the reaction on the middle support, let's say R number 2. So this is by summation of forces vertical equal to 0, upward forces to be positive. So that will be the same as R1, 60 plus R3, 60 minus the load. We have 40 all over a span of 8 meters plus R sub 2 equal to 0. So computing for the support reaction on the middle support. And is equal to 200. Is equal to 200 kilonewtons. Okay, so we have now the support reactions. We can now go draw the detailed shear and moment diagram. Okay, so let us draw the shear and moment diagram. Okay, starting with the shear diagram. So, starting on the left end, we have a positive reaction here which is 60 kilonewtons. Then we have 60 minus 40 times 4. Okay, that's equal to negative. This is equal to negative 100. And this is first degree since your loading is a 0 degree load. Negative 100 plus 200, that gives us a value of 100. Then again, 100 minus, this 100 minus 40 times 4, this is obviously negative. We go with a negative 60. Negative 60 plus the support reaction 60 will have a value of 0. So this will be our shear diagram. Okay, for the moment diagram, so on this triangulation, so let's say this is x, this is obviously 4 minus x. So by ratio proportion of similar triangles, we have 60 is to x is equal to 100 is to 4 minus x. This is equal to 1.5 meters. Alright, so we have this dimension is 1.5. So 4 minus 1.5 is, this is 2.5 meters. So starting on the left end, so obviously for a heel support, we have a 0 moment, okay, plus this area. What will be that area? That is 60 times 1.5 over 2. That is equal to positive 45. From positive to 0 shear, so opens downward with a magnitude of 45. Then we have 45 minus this area. Let us check if this will be the moment at 2. That is, we have 45 kilonewton meter, okay, minus, that is a negative area, 1/2 of 2.5 times 100. So let's check if we are to arrive with that moment, the moment number 2, which is negative 80 kilonewtons. That is 45 minus 0.5 of 2.5 times 100. So we have a value, this is correct, we have a value of negative 80 kilonewton meter. So from 0 to negative opens downward, this is negative 80. Negative 80, this is 100, this is 2.5, this is 1.5. Negative 80 plus 100 by 2.5 over 2, we have positive 45. 45 kilonewton meter, then minus, obviously 45 times 1.5, or minus 60 times 1.5 over 2. This is obviously equal to 0. So this is our moment diagram. So this is our example for the first example for the 3-moment equation. Considering that we don't have a settlement and EI, or the moment of inertia of the beam, is constant.